Okay, our topic today is fitting exponential models to data. This will be our last section specific towards exponentials, but we've done a good job with them so far. We've learned about exponential growth, exponential decay, as well as continuous growth. So now we're going to say, if we just give you data, how are you going to actually determine whether it is data that fits an exponential model? So, looking at, remember we have, as I said, annual growth rate. We could have a decade growth rate, and we're going to use our calculator to do a best fit, similar to what we did with a linear model and quadratic model. So remind you again, y equals ab to the x could represent an exponential growth if b is greater than 1, and exponential decay if our b value is between 0 and 1. Now, most of the time your factors for the percent of growth or decay are an annual growth factor. However, if they are a decade growth factor, then you want to think of b to the 10th. Okay, it's the annual growth factor basically taken to the 10th. There's not going to be too many problems that require a decade of information, but you'll see in the work. It's more or less, think about it as a period of time, like we've been doing on some of our other ones. So let's start with using the calculator to input the data and evaluate the data. So you probably remember our function where we go stat, calculate, and you had some choices, linear regression, quadratic regression we've done, and now we're going to have, it'll be the case of exponential regression, EXP, if you know your data does show characteristics of an exponential growth or decay situation. So what kind of data are we going to talk about? Well, here we go. The U.S. Bureau of Census has estimated that the population of Cuba will be 11,613,000 in the year 2000 and 12,795,000 in the year 2020. What annual growth rate is assumed between 2000 and 2010? So you have basically two sets of data. You have a year, so let's think of it that way. The year 2000 was with the 11,613 million, and 2020 is the 12,795,000. All right, so if we think of this like our table, time is our x and y is our outcome. So if we say this, we really have two ordered pairs. So if you go to your calculator and we do the EXP combination, you should be putting in, and follow me with yours if you have it, we should go to Stat, Edit, because we have some lists that we're going to put in. Make sure you're entering your data in L1 and L2. L1 are our years, and we're putting them in as is. And so 2000 and 2020. Make sure if you have any other data, you clear it out, delete it, because we do not want it in our list. We want it clean. And then the L2s, we need the bigger numbers, the population. 11,613,000, and then 12,795,000. And again, delete any extra data. Okay, now once you have those data in, supposedly those are your two pieces that make your curve, and they're telling us we have what annual growth should we assume. So now go to Stat, Calculate, and down off the screen, so arrow down, I believe your choice for exponential regression will be choice 0. So choose that. Cursor's blinking. Do you really want exponential regression? Say yes, or hit the enter, and you should see that the calculator spits out your regression equation, which we know is y equals ab to the x. So if I'm saying this is what my calculator spits out, here's my calculator screen. And then it has an a value directly under that. Ours is 716.73400014. As a b value under that, 1.004858229-ish. And then it also has the r squared and the r, because you probably have left your diagnostics turned on. We are not going to be using those as actual values in our work, but now if we said, what's the annual growth rate model that we can assume, we're probably going to come back to this problem and say y equals 716.73, round to the tenths or hundredths would be appropriate. Our b value would be, if we go tenths or hundredths, we're getting a 1. So in this case, I'm going to keep it a little bigger. I'm going to go thousandths, 005, because I don't want it to look or put any more error into the problem than necessary, and then to the power of x. So right now, that is an exponential growth equation that appears to be fitting this data fairly nicely. And again, this is because we did exponential regression choice 0 on your list. Okay, with that, the only other possibility would say the population of Cincinnati, Ohio was approximately this amount.
Good morning, staff. Just a reminder that we will be...
So back to the problem. Population of Cincinnati, Ohio is given for the year 1960. And its population for 1990. It says find the exponential model for this population between these years, and then it says also what would be the population in the 1998. So again, sort out your information. We have some years, 1960, and the 503,000, and we have 1990, and we have 364,000. So right away you're looking at this and saying, wait a minute, their data is definitely not going up, so we're expecting to see a definite decay situation. That starts telling you some things about your B value in your model. Okay, so we need to do that first. So again, go to your calculator, go to Stat, Edit. Our years, we're putting them in as whole values. There's nothing to tell us not to. In 1990, whoops, don't mind me, I can't type very well. Okay, so we got 1960, 1990. And again, your population is a little smaller than our last problem. Then go back to, once it's entered, go back to Stat, Calc, and our choice again is 0 for exponential regression. We're expecting a decay. Yes, this is what we want. And this time we're getting a value, a 7.563-ish, a B value of approximately 0.989-ish. R squared is 1, and R is -1. Now we won't be using those for our diagnostics, but we definitely need these two because we have one more question we're supposed to be saying. What is the population in 1998? So if we go back and write our equation now, we're looking at y equals 7.563. And this was, e to the 14th. So make sure you're putting that whole number in. And then we have our growth factor of 0.98, so it's decaying definitely, and we've got an x. So all we have left to do is use that model, put our new data in, and we're looking at the year 1998. Now remember, 1998, going from here to here, is our determining factor, because since 1960 was our original amount, 60 to 98 is a period of 38 years. So we should be substituting into our equation at 38. So let's go 7.563 times 10 to the 14th power times 0.989 to the power of 38. And I think we have a slight problem. So yeah, this thing's supposed to be decaying. I think I have an error in my data entry. So go ahead, and it definitely should be a little smaller than the 364 value. I have an error in my data entry, but if you do this one, we're looking to say, what is 1998? Definitely use that as your start. We'll share in class as to what that actual value should be, seeing what you got. So that's the last part for exponential decay and exponential work. We'll be moving on to logarithms next.